So yeah, hi everyone. Today we have the pleasure to have Catarina Cosme from University of Coimbra, and she will talk to us about temperature evolution in the early universe and freezing at stronger coupling. So please, you have the floor, and feel free to ask questions during the presentation.
Yes, sure. So first of all, hello everyone. Thank you a lot, Jordan, for this invitation, and it's always a pleasure to be here in Aveiro. Actually, when I was a PhD student, I used to come here at least once a week. So I know the environment, I know the people, and it's always a pleasure to be here. Yes, today I'm going to talk about this project, the temperature evolution in the early universe and freezing at standard coupling that was done in collaboration with my colleagues here, Oleg Lebedev, who is a professor at Helsinki University, and also Francesco Costa, who was at the time a PhD student at Göttingen University in Germany, and now is a postdoc in Prague. And so this talk will be based in these two papers here. But before going to the main topic of my talk, I would like to say a few words about dark matter and dark matter production mechanisms. Then I will introduce our model, this freezing at stronger coupling. I will discuss its phenomenology, the detection prospects, in particular the direct detection ones. And then I would like to tell you a little bit more about this, how the temperature evolution of our universe can affect the dark matter production in our model. And finally, I will conclude. So, the first thing that we can think, or that can come to our mind when we think about dark matter, is precisely why do we think that dark matter exists? And how do we know that dark matter exists? And in fact, there are several phenomena that point towards the existence of dark matter. For instance, we have the case of the galaxy rotation curves. So the galaxy rotation curves are just a plot of the orbital velocity as a function of some star or gas within a galaxy as a function of its radial distance from the galactic center. And from what we observe from the visible disk, we would say that these galaxy rotation curves will go down as we go far away from the galactic center towards the halo. And this is very intuitive. We can do it just by using Newtonian mechanics. We know how to compute the orbital velocity of some object in the universe, and we know that it goes with the square root of 1 over the distance from the galactic center. However, what we really observe is that these galaxy rotation curves are not going down as we go far away from the galactic center, and instead of that, they become almost flat. So this means that there must be something else, some kind of non-luminous matter that we cannot observe, but it is accounting for these effects. And we call this non-luminous matter dark matter. Also, we have the information that can come from the baryon acoustic oscillations of the cosmic microwave background, CMB. So these baryon acoustic oscillations are just small ripples in the CMB due to temperature fluctuations, whose big structure that we can have here only exists if we add dark matter to the model. And probably the best evidence for the existence of dark matter is the so-called bullet cluster that is depicted in this picture here. So this is a composite image, and the bullet cluster is a huge cluster of galaxies that was formed when two large clusters of galaxies collided. And therefore, in this picture, in these pink clumps here, we can see where the hot gas of the system is localized. So the baryonic mass of the system is localized here, and it was discovered using, for instance, the Chandra X-ray telescope. And then the idea was to find where the major part of the mass of the system was localized. And then using other telescopes that would see in another range of the electromagnetic spectrum, and also using the so-called gravitational lensing effect that you know probably what it is, but it is when we have light traveling across the universe and light is distorted due to the intervening matter. So the researchers would find that the major part of the mass of the system is localized in these two blue regions here. So we can see that the pink and the blue region they do not overlap, which means that the major part of the mass of the system is not baryonic mass. It must be something else, and we call this something else dark matter. Also, from the observations of CMB and large-scale structure, we find that dark matter makes up about 27% of the mass energy contents of the universe, while baryonic matter and radiation makes up only 5%. And then we have this huge slice of the energy budget of the universe that is dark energy, and it is responsible for the recent accelerated expansion of the universe. And also, We know that dark matter candidates should fulfill some requirements. For instance, we know that it has to be very stable, or at least long-lived. Otherwise, we wouldn't have dark matter by now, it would have decayed. Also, this dark matter candidate has to be non-relativistic in order not to spoil the structure formation. We also know that a dark matter candidate has to have a very small interaction with the electromagnetic field, or no interaction at all, if it's dark. And of course, the viable dark matter candidate, its abundance must match the abundance of dark matter that we observe in the universe. And we know that from this list, nothing in the standard model fits the description. So dark matter should consist of a new particle or a new set of particles. And okay, it is true that we already know a few things about dark matter. We know that there is evidence for the existence of dark matter. We know the amount of dark matter today that we observe in the universe. And we know more or less how a dark matter candidate should look like. However, there is a fundamental question that still remains, that is, what is dark matter made of? What is its nature? And the honest answer is that we still don't know, despite the large number of dark matter theories that you can find in the literature. And so my talk today will be about one specific dark matter theory. But before going to the main topic of my talk, I would like to say some words about one of the most popular dark matter production mechanisms, where dark matter is produced thermally, so that we can see its shortcomings and why we need alternatives to these more mainstream dark matter candidates. And so, one of the most popular and well-known dark matter production mechanisms is the so-called freeze-out mechanism. So the freeze-out mechanism assumes that dark matter, which I represent here by this X, was in thermal equilibrium with the standard model particles in the early universe. So this means that standard model particles were producing dark matter, and dark matter was producing standard model particles. There was this thermal equilibrium, they will share the same temperature, and I think that the best way to explain to you how the freeze-out mechanism works is to show you a plot. And so in this plot, we have the yield of dark matter, that is just the ratio between the number density of dark matter over the entropy density of the universe as a function of this X parameter. And this X parameter is just the dark matter mass over the temperature. So this dashed line that you can see here corresponds to the equilibrium yield of dark matter. This means that if dark matter is in thermal equilibrium with the standard model of particles, its yield should follow this dashed line. And then we have different colored lines responding to different final yields of dark matter, depending on the dark matter coupling lambda to the standard model particles. And if we want to build a plot like this, what we have to do is just to solve the Boltzmann equation that is stated here. So in order to do this plot, I assumed the simplest freeze-out case that we can have, that is just assuming having one standard model particle and a dark matter one, and I am just assuming annihilations and inverse annihilations of dark matter. And so in the left-hand side, we have of this Boltzmann equation, we have basically how the universe will evolve. Here, this H is the Hubble parameter, and then on the right-hand side, we have the collision term, and the collision term tells us how dark matter will be produced and destroyed. So this sigma V is the thermal average cross section, and this EQ stands for equilibrium. And so according to the freeze-out mechanism, initially dark matter was in thermal equilibrium with the standard model particles. We can see that the yield follows this dashed line, and just when the interaction rate is capital gamma between the dark sector and the visible sector becomes smaller than the Hubble parameter, which means that virtually no particles have been created or destroyed within a Hubble time. At that moment, dark matter will decouple from the thermal bath and its abundance becomes constant. So we say that at this point, dark matter has frozen out. So since in this model, the typical cross-sections that will provide observed dark matter abundance are of the order of the weak scale, we call this dark matter candidate WIMPs, weakly interacting massive particles. And in fact, we can compute, for instance, the present dark matter abundance for the case of result. That is given by this omega x naught, and we can show that it is proportional to the inverse of the dark matter coupling lambda. So this means that smaller couplings will provide larger abundances or larger yields of dark matter, because the abundance and the yields, they are directly proportional. And that's something that we can see actually in this plot. So for instance, this blue one is the one that corresponds to the smaller coupling, smallest coupling of these three. and it's the one that is providing the largest abundance of dark matter. Of course, these compounds are extremely large, but it's just for illustrative purposes, don't mind it. So, actually, WIMPs are very popular, and almost all dark matter detection experiments were designed to detect them. But there is a huge problem, and the problem is that WIMPs have evaded detection so far, and now the parameter space of this WIMPs model is very constrained by experiments. And just to give you a flavor of what happens, I decided to put here 3 different WIMP dark matter models. So these plots came from this very recent and very good review on these WIMP dark matter models. And we can see, so in the left-hand side, we have the WIMP scalar dark matter through the Higgs portal. So this means that dark matter here is a scalar. Higgs portal means that it is the Higgs that makes the connection between the standard model and the dark sector. So it's a mediator particle. In the middle one, we have fermionic WIMP dark matter through the Higgs portal, and here in the right-hand side, we have scalar dark matter, but the mediator is a Z prime. That is very similar to the Z, but we included an extra U1 prime symmetry. But and so in these 2 plots, we can see on the y-axis the dark matter coupling as a function of the dark matter mass. And in this case, I have the dark matter mass as a function of the Z prime mass, but the information that we can get from all these plots is basically the same. So in this red line, corresponds to the parameter space of these models that can provide observed dark matter abundance, and the colored regions correspond to exclusion regions. It means that if the parameter space is inside this region, it is excluded. For instance, in purple, we have direct detection, the parameter space in this model that can be already excluded using direct detection experiments, like let's say Xenon. And so we can see that in all these models, the parameter space of dark matter is practically ruled out. Maybe in the case of the WIMP scalar dark matter through the Higgs portal in this region of the resonance, we can have still some hope of finding dark matter, but still the parameter space is very constrained. So maybe this means that the WIMP is waning, and maybe this means that we need to look for an alternative to this freeze-out mechanism. And yes.
So you said this red line is for the current abundance of dark matter?
Yes.
What if it's just a partial abundance and not the whole? Would it be worse, or can it go into other regions?
Yes, that is a good point, because these are the simplest WIMP models that we can have. Of course, that we can have a more elaborated WIMP models with different dark matter candidates, actually. But even in those cases, according to this review, and I believe it, because I know the authors and they are really good, so it will be very hard to explain the dark matter that we observe in the universe. It's really hard. In the case of WIMP, it's almost there, honestly. But okay, so now I hope I could convince you that we need something else, and an alternative to this WIMP mechanism that can be given by relaxing this initial assumption of thermal equilibrium. And if we do so, we can talk about the freezing mechanism. So the freezing mechanism assumes that dark matter was never in thermal equilibrium with the standard model. So this means that in the early universe, standard model particles will produce dark matter particles, but there is almost no back reaction from the dark sector, and the production of particles occurs mainly in this way. I think it's not working very well. I can pass here. Okay, so the production of particles occurs mainly in this way. And so this means that the dark matter production will be out of equilibrium, and it will never reach thermal equilibrium with the standard model particles. And again, I think the simplest way again to show you or to explain to you this freezing mechanism is to show you a plot. And we have again a plot with the yield of dark matter as a function of this X parameter. Dashed line corresponds to the equilibrium yield, and different colors correspond to different dark matter couplings to the standard model. If we want to track again the dark matter evolution, the number density evolution or the yield, we have to solve again the Boltzmann equation, and we can see that the left-hand side is exactly the same as the case of result, because it just tells us how the universe evolves, but the collision term is totally different. And it is different because the initial conditions of the freezing are completely different from the initial conditions of the freeze-out phase. And so here, for this plot, I'm also assuming the simplest case of freezing that we can have. That is assuming that we have a sigma particle, a generic standard model particle, that will decay into dark matter. So this capital gamma is the decay width. K1 and K2 are modified Bessel functions, M sigma is the mass of this sigma particle. And then according to the freezing mechanism, initially the abundance of dark matter is 0. And then the yield is increasing until there is no more energy from the sigma particles to produce dark matter. Or the number abundance of the sigma particles is so small that it cannot produce dark matter anymore. And at that point, the abundance of dark matter becomes constant, and we say that dark matter has frozen. So notice that in this case, the abundance of dark matter never followed this dashed line. It was never in thermal equilibrium. Since the typical couplings lambda here in this case are so small, so feeble, even smaller than the wind case, we call this dark matter candidate FIMS, feeble interacting massive particles. And actually there is a very important condition that must hold during the production of dark matter if we are in the context of the freezing mechanism. That is, all the interaction rates of that will contribute for the dark matter production have always to be smaller than the Hubble parameter. So if we are, for instance, studying some process to generate dark matter, if there is at least one process that does not respect this means that dark matter will not be produced via freezing. It will be produced via freeze out, but not freezing. So this condition, the freezing condition, must hold during the whole process of creation of dark matter. And again, we can compute the abundance of dark matter for the case of freezing, and we can show that it will be proportional to the dark matter coupling lambda. And in this case, we can see that larger couplings will also provide larger abundances of dark matter. And that's something that we can see here in the plot. So in this case, the blue one is the largest coupling and also corresponds to the largest yield of dark matter. So that is the basics of freeze-out and freezing mechanism. And this is just a summary plot, just to summarize everything I told you and to point out the main differences between these two processes. So freeze-out mechanism, dark matter was in thermal equilibrium with the standard model particles. Just when interaction rates become smaller than the Hubble parameter, dark matter will decouple from the thermal bath. In this case, the abundance of dark matter is proportional to the inverse of the dark matter coupling lambda, but the problem is that we couldn't find things weak so far. So it's a bit constrained now, a lot of very constrained, and some models are already ruled out by experiments. In the case of freezing, dark matter was never in thermal equilibrium with the standard model particles. The abundance is proportional to the dark matter coupling lambda, and from here we can see that to attain the same observed dark matter abundance, we will need smaller couplings when compared to the freeze-out case. And having smaller couplings, on the one hand, this is good because this means that FIMS can evade the stringent observational constraints that WIMPs cannot do anymore. But on the other hand, having such small couplings is also really bad because it makes a hell to try to detect this kind of dark matter candidates. But in any case, in our model, we decided to go within this freezing mechanism.
So can I ask, besides that just said, from the viewpoint of particle physics, I mean, such small couplings, I mean, are they well justified? Are they natural? Do they arrive? I know it's kind of a freak parameter.
Yes.
It looks like a very tiny number. You don't have these tiny numbers in say 7 also.
Yes, this will be natural, at least in these models of freezing. And actually, that's what we need, otherwise we'll never achieve the abundance of dark matter. Now, I know that they are really small. I will show you one way of increasing it. That's the topic of this talk. But like for detection experiments, it's almost impossible. If you have standard cosmologies, and by standard cosmology I mean, so you have inflation, then reheating, and then immediately radiation errors, it's impossible to detect. You can also think about non-standard cosmologies, like having early matter eras. I will talk a little bit about that next, but in that case, since you will have some dilution that comes from this early matter era phase, you will need for the case of freezing larger couplings. In this case, it's much easier to detect these kind of things. But the standard freezing phase, it's really hard. Although it can be motivated, okay, it's natural, but for detection, it's really hard. And even like the next generation of like the Earth detection is almost impossible. In case of the Higgs portal, I think it's the one that gives us the best prospects for direct detection. Like neutrino portals, very hard, but still, and even in direct detections. So when we think about dark matter annihilating, for instance, into photons, it will be really hard in the case of Higgs.
So
But
your main work is about detectability rather than the theoretical support of the model.
But okay, so I hope I convinced you that freezing mechanism is a good alternative to this freeze-out case. But as I was telling you, it faces two important challenges. And one of them is that, okay, it has really small couplings. It will be very hard to prove this dark matter candidate, even through direct, indirect, or collider experiments. And also, it assumes that there is zero or negligible initial dark matter abundance in the universe, which may not be completely true, as we will see in the next slide. But okay, so the big question that everyone that works on FIMP wants to answer is, how can we probe FIMPs? Is there a way of probing such elusive dark matter candidates? But before trying to answer this question with our model, let me just take one step back and tell you a little bit more about this second bullet that we have here, about this assumption. Because in fact, assuming that there is zero or negligible abundance of dark matter in the early universe can be a very strong assumption in a world with gravity. Because we know that in the early universe, there are many processes that can generate stable scalars only through gravitational interactions. It can be through at a classical or quantum level, but it is possible. And the thing is that, so these dark relics or these stable scalars, they can be seen as dark relics because if they are stable, if they have the suitable dark matter abundance, and if they survive until today, they are viable dark matter candidates. And this can happen right during inflation. For instance, we can have some scalars, and the scalar fluctuations will provide like the initial conditions for dark matter candidates. It can happen right after inflation in this period that is called reheating. So the reheating is when the inflaton transfers its energy to the standard model particles. Usually we have a first phase of preheating that is called preheating, and during preheating the inflaton will start to oscillate around the minimum of its potential, and when it oscillates it can generate a huge bunch of particles. And of course we can also think about the inflaton decay. And the thing is that, okay, all these processes will generate particles. Usually they have very feeble couplings, they will never attain thermal equilibrium. But the thing is that they will produce a very important background for non-thermal studies, because if they are produced non-thermally, we have to take them into account. And actually we have to sum all these processes, or all the abundance of dark relics that can come from these processes. And again, even if there is no direct coupling between, for instance, the inflaton and other scalars that can exist in the universe, there is always gravity. And we cannot turn off gravity. And therefore, the production of particle, the gravitational production of particle will occur anyway. And just to make this point and to tell you a little bit about these processes that can happen, I decided just to talk very briefly about two of these processes that can generate dark relics in the early universe. But I will not enter into much detail because it can be much more like complex than this. So here I just had the timeline of the events. We have inflation that will end at some, let's say, temperature T end. Then we have this reheating phase where the inflaton transfers its energy to the standard model particles in particular. And then inflation or the reheating will end at this TR temperature, the reheating temperature, and this marks the beginning of the usual radiation era that we all know. But we know that right during inflation, we can have some scalars other than the inflaton. There is nothing that forbids the existence of scalars, actually. The only thing is that during inflation, generative density of these scalars has to be subdominant because the field that will rule inflation will be the inflaton. But in any case, we can have these scalars. Usually they also, the self-interactions are very small. But the thing is that we know that any scalar field during inflation will exhibit quantum fluctuations that will get stretched and amplified by expansion. And so what happens is that, so we can have this scalar field, we will have these scalar fluctuations that will be amplified. And these scalar fluctuations will set the initial conditions for this field for it to start to oscillate when its mass is of the order of the Hubble parameter. And it will always happen. Usually it starts to oscillate after inflation, but the thing is that the inflationary dynamics can set these initial conditions for this field. And so what happens is that during inflation, we can have oscillating scalar fields that can survive until today. And in particular, we can show that any oscillating scalar field, it will behave like non-relativistic matter. So we have a stable scalar, it is non-relativistic, and if it has the correct dark matter abundance, it is a viable dark matter candidate. And again, we don't need any coupling, direct coupling between this scalar S and the photon. And actually, this is what I studied during my PhD, this kind of dark matter candidates that were, whose initial conditions were set by inflationary dynamics. And also, I had some works with other people from Helsinki. So this is one of the processes that can happen, but there are more. As I told you, right after inflation, we have the preheating. So the inflaton will start to oscillate around the minimum of its potential. And what happens is that if we have, for instance, a direct coupling to other scalar, the fluctuations, since the inflaton is oscillating, the fluctuations of these other scalars will be amplified. And what happens during preheating is an explosive production of particles of these scalars through a process that is called ferrometric resonance. That is more complicated, very complicated actually. But the thing is that the occupation number of these scalar particles will have a huge growth, and we can have lots of dark relics. And again, even if there is no direct coupling between the inflaton and other particles, the inflaton is oscillating, and consequently, the scale factor and the Hubble parameter will oscillate as well. And this can induce some terms in the Lagrangian of this form. So phi is the inflaton, S is the scalar, and these terms can be seen as the annihilation of inflaton into these S particles. And this actually, I don't know much more about this process. I read the work by this Japanese group, and also Lev Lebedev worked a lot on this gravitational production during preheating, and this can happen. So the thing is that we can end up with a huge amount of dark relics, and that assumption for freezing maybe doesn't work. So now the question is, okay, so how can we get rid of this excess of dark relics and save the assumption for freezing? And actually, interestingly, one of the possibilities relies precisely on this behavior of the inflaton after inflation. So as I told you, the inflaton will start to oscillate around the minimum of its potential. And in particular, if it is a quadratic potential, and usually in most inflationary models, we can approximate the minimum of the potential as a quadratic form, we can show that the inflaton will start to behave like matter. So what happens is that right after inflation and before the usual radiation era, we can have these early matter eras. And these early matter eras are very interesting in cosmology. In this case, it comes immediately from the inflaton, but we can have other sources for that. But the thing is that during this early matter era, first the Hubble parameter will scale with the scale factor in a different way from the radiation era. And also, since this early matter era is not a relic, it has to decay at some point. And when it decays, it will inject entropy in our system. And this entropy injection will dilute any relic, any species that we can have during this phase. And therefore, the relics that were generated at the early universe can be washed away. And so there are many features that we can study about these early matter eras, but for instance, we can actually compute the dilution factor, that is this delta n, that is related always with the Hubble parameter at the end of inflation and at preheating. And usually the larger the delta, the longer the early matter domination era, and also larger dilutions. And it is also interesting because when we have these early matter eras, we can have very low reheating temperatures for our universe. And actually, this can be very useful for our purposes. So with this, I showed you that, okay, these dark relics that can be formed will be washed away anyway, but...
Sorry,
yes.
can you hear me?
Yes,
Okay.
yes.
I have one question. Like, it makes sense to talk about the temperature before the inflaton decays. Like, for instance, It's the temperature before the inflaton decay is 0,
Well,
or what is the temperature?
yes, it makes completely sense because in practice, we don't really have a huge amount of standard model particles to generate the temperature. Probably here, the best nomenclature will not be temperature, but it's scale factor. It should be an AN and not a TN. So if we think about the same process in terms of the scale factor, it's more correct, yes. But I mean, you can always think that we have still residual standard model particles and some kind of temperature, but yes, doesn't make perfectly sense to have a temperature before the complete, or at least the photon is decaying. But in any case, yeah,
Okay, no, I got it.
yeah. Yeah, but in any case, so during preheating and, well, I'm not sure about the scale of time, it can be very fast or not. But, well, we are already generating some radiation, so at some point we will have some temperature. But yes, to be completely rigorous, and actually that's what we did. We do all the reasoning and all the calculations assuming the scale factor and not the temperature.
Do you know some reference that you do it?
I don't know who is talking, but I can send you some references
Okay, it's
after.
Vinicius, yeah.
Okay, so then you can text me or send
Okay,
an email and I will. Okay,
okay, thank you.
no worries. Okay, so with this we get rid of our relics and also we can have low radiating temperatures for our model. And actually, this is very nice that we can have a motivation to have low radiating temperatures because in our model we decided to study the dark matter freezing production, but just in the range where the dark matter mass is larger than the reheating temperature. And why did we decide to study this? And we decided to study this because if the dark matter mass is larger than the reheating temperature, this means that the only particles in the standard model that will have energy enough to produce dark matter will be the ones that are at the tail of the Boltzmann distribution. And so this means that if these are the only particles that can generate dark matter, the dark matter production will be Boltzmann suppressed. And we will see the Boltzmann suppression term in the yield of dark matter in one expression that I will show you next. And I will show very few expressions, no worries. But yeah, we can see this Boltzmann suppressed dark matter production. And therefore, this means that if the production of dark matter is being suppressed, in the case of freezing, we will need larger couplings in order to compensate for this suppression and to achieve the observed dark matter events. And therefore, if we can have freezing with larger couplings without compromising the non-thermal equilibrium condition, this means that maybe this model can become testable in detection experiments. And that's what I'm going to tell you now. So in this model, we decided to study the simplest case that we can think of, that is the scalar dark matter through the Higgs portal. Here I just have the potential of our model, and S will be the dark matter mass, lambda H the dark matter coupling. This H here is the Higgs and not the Hubble parameter. And again, we are studying the freezing production in this range, where the dark matter mass is larger than the reheating. Then what we have to do is just apply the recipe that I told you in the beginning. We have to solve the Boltzmann equation, and we can show that in this case, the only processes that will contribute effectively for the dark matter production or destruction will be the Higgs annihilating into dark matter, and then the inverse process. So this capital gamma here corresponds to a reaction rate density. So here we have the production of dark matter, and here we have the annihilation of dark matter. And in our computations, numerical ones, we use always the full Boltzmann equation, but of course we can think about some limits. And for instance, in the case where the annihilation dark matter part is inefficient, we are just left with the production one, and then we can solve the Boltzmann equation. Actually, we can do it analytically, and we can find the yield of dark matter for our model. And notice that it will depend on the dark matter coupling squared. And also we have this exponential factor here with ms over tr in the exponential, which means, and this is precisely the Boltzmann suppression term. From here we can see that the yield of dark matter is being Boltzmann suppressed. And if we assume that our dark matter candidate makes up all dark matter in the universe, we just have to substitute the value that we observe of dark matter here. And if we do so, we can get a relation between the dark matter coupling, the dark matter mass, ms, and the reheating temperature. And of course, that if the annihilation term is inefficient, we are in the freezing case. And now you can tell me, oh, okay, but you said that we can have very large couplings, but we have a coupling of order of 10 to the minus 11, which is extremely small. And yeah, that is true, but the smallness of this prefactor can be easily compensated by the values of this exponential here. And in this case, in freezing, we can have couplings of almost order 1, or 10 to the minus 1, which is completely amazing because if we are considering vanilla freezing, so reheating temperature is too large, the couplings will be of the order of 10 minus 11, which is impossible to detect. And so in this case, at least we can have larger couplings. But again, as I told you, in our model, we studied the full Boltzmann equation, and it is also possible in our model to have results. But for that to happen, the reaction rates of the production and annihilation, they have to be equal and active at the same time for a sufficiently long period of time. If that happens, we can have results. And just for you to get a flavor of this, let me just show you a couple of plots where we can have the freezing mechanism in our case or the results. So in the left-hand side here, I have the reaction rate of annihilation of dark matter in yellow, the production rate of dark matter in green, and then in blue, I have a term that contains the Hubble parameter. So basically, if we want to know whether a process is efficient or not, we have to compare with this Hubble parameter term. Basically, if it is above it, this means that reactions are really fast, so dark matter is being produced or annihilated. If it is below, it's not very efficient. And in this case, for this parameter space, for instance, this is just to give an example. We can see that the annihilation rate is always smaller than the Hubble parameter. It was never larger than it. It was never equal to the production rate. So this means that in this case, the annihilation rate is never significant. And in this case, we will have the freezing regime. And actually, you can see here the plot of the yield as a function of the temperature, and it has the same shape as the freezing plots that I showed you in the video. We can have also another case, for instance, here for this parameter space, you can see that here the annihilation rate is slightly above the Hubble parameter, but it was not equal to this production rate for a sufficiently long period of time. So in this case, we still have freezing, but it will be very close to the freeze-on state, and this can happen in our model. And then we have the case, as we see, the yellow line is equal to the production rate above the Hubble parameter for a sufficiently long period of time. In this case, this means that the system has time to thermalize, and we can get the freeze-out regime. Those plots is here, as you can see in this right-hand side. So we can have both freezing and freeze-out in our model, but we are more interested in the freezing case. And okay, so in this plot, I represent the dark matter coupling as a function of the dark matter mass. So these solid colored lines correspond to the parameter space of our model that can provide the observed dark matter abundance. This purple one corresponds to the freeze-out case, and the almost vertical ones correspond to the freezing case with different reheating temperatures. So this dashed line corresponds to the neutrino floor, and then we have this shadow region in gray that corresponds to the parameter space that can be probed using direct detection data from LZ experiments. And so these vertical lines, they follow precisely that expression for the dark matter coupling that I showed you in the beginning. And we can see that, in fact, for the freezing case, we can have couplings of order 10 to minus 2, here almost order 1. And the thing is that, or the main message that we can take from it is that, okay, so our model can already be probed using current direct detection experiments. And again, this is a really remarkable feature and a really remarkable result, because usually, if we are thinking about models of freezing where reheating temperatures are too large, the couplings 10 to the minus 11 will be here. That is completely impossible to detect right now. And in this case, we could see that, yeah, it is already possible. And there are some other next generation of detection that will be able even to probe lower couplings. And okay, so I could end up here and could say, okay, we have a nice model for freezing. But let me just discuss just one more thing.
Okay.
Yes.
Would you say some words about this direct detection experiments, how
Yes.
they work? And
Yes.
I don't know if you're gonna say that, if you're not.
No, I'm not, but I can. It's not my field, it's more, but basically, for the outside, they use huge chains of, I think it's xenon, liquid xenon. And so basically what they want to catch is, we have dark matter passing in the earth. It will kick the nucleus of xenon, and then you will have some kind of, it could be some recoil or some thermal energy. Basically, I think I'm not wrong saying that. And then if they detect it, they can say that they detect dark matter. And there are many experiments that use these noble gases because they are inert, they are more stable. Like they can use xenon in the case of LZ, but there are others that use argon. Which one? I think the most popular are xenon, that is LZ, xenon and time. Darwin uses as well also xenon. But there is one that uses argon that I don't remember the name now, but I can look it for you. But yes, usually what they want is to get the kick of dark matter in the nucleus and see like I don't know if I can say displacement or some thermal energy that will result from that.
So, but couldn't something else cause the heat? Why does it have to be dark matter?
Well, this is a little bit more, I think they will have ways to distinguish. For instance, this neutrino fog. This neutrino fog actually, it's a line that is very important because it is the limit. Until here, we can distinguish the background of dark matter from the background from neutrinos. And I think that for this case, if we are above the neutrino floor, they could say that, okay, this is dark matter and it cannot be any other particle. Here, it becomes more difficult.
There's a confusion.
There is a confusion, you can disentangle like the background coming from the neutrino recoils for dark matter recoils. But still, now I knew some time ago that they are.
Mass is very different, right? So you're talking about masses
Yes.
of 1 TeV. So
Yes.
neutrinos will have, well, depends.
Depends on the model, yes. It depends on the neutrino that you want to catch.
It could be an unknown neutrino.
No, but the thing is that, okay, here I'm showing these large masses. But still, in this model, it also works for lower masses that will be, I don't know about MEV, it depends, because then there are more details that we have to take into account, but it can be very liable as well in the case of. But even in the masses, I think it will be very difficult to disentangle these departments. And I know that now there will be next generation of detectors that will be able to, for instance, you know that you have an angular distribution for the neutrino flux, and then you have another one for dark matter, and they will be able to do like directional disentanglements and say, okay, no, this comes from neutrinos and this comes from dark matter. But I don't know if it is operating yet, but I know that it exists. It will be really nice, honestly, because then we can go even lower in the energies for the couplings. But yes, but I don't know much about that part because it's more experimental and I'm more theoretical. But yes. So as I was telling you, okay, I could end up here, but there is another stuff that I would like to discuss. That is the flow. Okay, so far, basically what we did in this first paper and this first work was considering that dark matter was produced mainly in this branch, and in particular, very close to the reheating temperature. But the thing is that we know that there is more story for the temperature of the universe below the reheating temperature. Actually, we can have really large temperatures. And what we did in our first paper was, okay, we are going to neglect all dark matter that can be produced before the reheating temperature or in this branch. And we thought it would be a nice assumption. We were not completely sure, but Oleg was completely sure actually. But okay, it was not for me and for Francesco really, well, maybe we cannot neglect it. And then in the first talks that we gave about the topic, there was at least one person that would ask, oh, but what happens for temperatures before reheating? And actually one referee was really insisting on that, and we said, okay, let's do a very careful study. And so in this second paper, what we wanted to do was to study the evolution of the standard model temperature and see if we would have any differences with respect to the previous plot that I showed before. If it was really important to consider dark matter that was produced here or not. And so, to talk about the evolution of the standard model temperature in the early universe, first there is one thing. We don't really know what happens during that process and how the inflaton transfers its energy to the standard model particles. It could happen that in the early universe it was just in one step, which means that, so in this plot I have the energy density of the inflaton in blue, the energy density of the standard model in yellow. And so in the early universe, the inflaton is transferring its energy to the standard model, we will have radiation. And this is probably a plot that you've seen before. So the inflaton is also starting to decay. So the energy density of the standard model will reach the top, and we know that is radiation, so it goes with that temperature to 4. We will have a maximal temperature for the universe. Then it increases because it will redshift, and at some point the transfer of energy of inflaton is complete, and we have the reheating, and then we just have radiation in our universe. But the thing is that in this scenario, we will have maximal temperatures that will be much larger than this reheating temperature. And this can be okay, but we were thinking about temperatures that would not be that high, so that we can have dark matter masses much larger than the reheating temperature. And in this case, for the freezing, it will be almost impossible to have huge masses and contain and the freezing condition hold, and this happens. So this scenario is not that good for us. So maybe in this case we can have freezing for sure, but it will be the usual freezing with huge temperatures and sensitive, very large temperatures. But there is another possibility. Again, we don't know what happens in the early universe, so it may happen that the transfer of energy of the inflaton occurs in two steps. So first, the inflaton transfers its energy to an intermediate particle, for instance, right-hand neutrino, and then the right-hand neutrinos will transfer its energy to the standard model, to the standard model particles. In this case, I have the energy density, again, in blue of the inflaton, in yellow of the right-hand neutrino, and in green we have the standard model case. And we can see that if this is the scenario in the beginning, in the early universe, the energy density of the standard model particles is constant. It's constant until the decay of the inflaton is complete, and then also the energy density of this right-hand neutrinos is complete. And in this case, we can have a maximal temperature that would be more or less the same, of the same order of the reheating temperature. And again, even if we are going to consider all the temperatures that are before the reheating temperature, at least they will never be too high. And therefore our assumption for Boltzmann suppression freezing will happen anyway. And this is a scenario that we are thinking. And again, it's completely viable to have this one or that one. And we can think that this is what happened in the universe. And actually, if the decay width of the inflaton is very close to the decay width of these right-hand neutrinos, what happens is that these two particles will decay at the same time, and in this case, the maximal temperature will coincide with the reheating temperature. And so just to show you the plot in terms of the temperature, so basically in our first paper, we are studying dark matter that was produced in this branch. And now to update it and to be completely rigorous, we have to compute the dark matter that was produced during this branch as well. And that's what I have here in this expression, but basically what is important is that this new yield of dark matter will be exactly the same as the yield of dark matter that we found in the first paper by corrected, and it is corrected by this factor ms over Tmax. But again, this Tmax will be very close to the reheating temperature, so using Tmax or TR is exactly the same. And just to conclude, let me then show you the updated plots. Here I have exactly the same, so the same parameter space that can be proved. Dark matter coupling is a function of the dark matter mass. These things or these thin lines correspond to our first paper, to the result that we found in our first paper, and the solid ones correspond to the updated ones. So taking into account all dark matter that was produced before reheating. And we can see that Oleg was right, and actually these updated results will just translate into a shift, a very small shift to the right of our results, but there is no, the conclusions remain unchanged. And actually, this means that for a fixed reheating temperature, we will need in this new paper to increase the dark matter mass by about 5%, which is nothing. Okay, so still the conclusions didn't change, even taking into account the thermal or history of the universe before the reheating. And then just to finish, I told you that, okay, dark matter or dark relics can be abundantly produced in the early universe, but if we have an early matter era, it can dilute it. And in particular, with early matter eras, we can have lower reheating temperatures for our universe. Having lower reheating temperatures is very nice because we were studying, or we would like to study the Higgs particle dark matter produced via freezing in the case where the dark matter mass is always larger than the reheating temperature, and we have a motivation to have lower reheating temperatures. We've seen that in this case, dark matter production will be also suppressed, so we need larger couplings to compensate for it. And then we could see that in this case, dark matter can already be proved using direct detection experiments, and there are some forthcoming direct detection experiments that will be able to prove even lower dark matter couplings in our model. And that's it. So thank you all for your attention.
Thank you very much for the talk and also for keeping time. So actually, I will give floor for questions, but I have a small one and it's related to one thing that's there, so I may start. So it's the same kind of experiments that would detect the dark matter in that case, so the films, then the ones that is for the waves.
Yes.
Right.
Yes, because in this case, we can already reach, let's say, some energies to find things. But yes, but yeah, that is true. So this Xenon and ton is already an update because you have Xenon 1 ton, Xenon 10 ton, and those were just designed to detect winds because at that time they didn't even know that things could happen.
Thanks. So are there questions?
Yes. That's kind of question. And how about in terms of, dark matter distribution, galaxies or clusters? Would there be any difference in terms of observability of WIMPs to FIMPs? Would there be some sort of, let's call it astrophysical signature that, you could help distinguish the models?
The model.
Yeah.
Okay. Yes.
Because you're looking just at the kind of example, well,
In this case, because
Type of
actually you
experiments,
can
right?
also look for indirect detection in this case. And indirect detection will be always like to have dark matter and everything to float. And you will have some telescopes like Fermi, and they will look for it, or for some particular line like there is this 511 EV or KV line, for instance, was very popular many years ago. They thought that it would be a signature of dark matter. But in terms of distinguish the WIMP and the FIMP in this case, I'm not really sure.
You may cluster in a similar way for structures, for instance.
Yes, I don't know much about the scale structure formation, so I don't know. Maybe there could be some differences, but I cannot tell you what they would be.
But people are looking to
Yes,
that.
I think they are looking for it. Actually, they are looking for instance, this, and they are doing this for things, and probably they will start doing for things, that is dark matter capture in some planets, for instance, and that would be something astrophysical that you could see, you have to take into account the capture rate and everything, but they are doing it for things, for weeks, thinking about they can be captured in some planets or like Jupiter. There's one paper where they talk about it. And yeah.
But only planets, not stars, why just planets?
I think planets because it would be closer to us.
Solar
But it
system
could be
kind of
solar
experiment.
system, yes, yes.
In the sun?
In the sun, probably, but I'm not sure about it.
Okay, just an idea. Okay.
Yes.
Thank you.
No worries.
More questions? Maybe on Zoom, are there any questions? Doesn't look like it, feel free. So maybe another small one that
Yes.
I'm not sure if I understood. So you said that you need the particles that will decay into dark matter to be not very abundant in the universe.
Sorry.
Yeah, I think towards the beginning, for the generic ideas, you said that the particles that decay into dark matter should not be too abundant now in the universe. Is that right? Or
Like this, the assumption, I don't know if it is the assumption of freezing, that there is no full abundance of dark matter or what? Or those dark matter that can be generated in the early universe, they're not abundant.
no, I think it was for freezing, but I'm not sure. It was towards the beginning, maybe if you can.
Yeah, we can go.
I was just wondering at some point if this would be particles from the standard model or if this would require additional.
No, usually no,
Particles.
it's particles from the standard
Oh,
model.
okay.
Yes, usually there are no, here is already results. But yes, usually for freezing, we think about standard model particles producing,
Okay.
not other exotic ones.
Okay, thanks. No more questions? So Catarina is still here today and so you can interact. So we'll also have lunch now. And we're thinking of having dinner together tonight. So I send an email after lunch so that you can tell me if you're interested to join, and then there will be more information on the precise location when I know how many we are. But it will be in town as usually, to be accessible from here. So thanks a lot.
Thank you.
We just meet in a few minutes to go for lunch.
Okay, thanks. I just need to go with my.
Yay, we are all going to, I just stop all of this. What's the